Hello, welcome to the online course of IIT Madras. I am Shankara Raman from the Department of Chemistry, IIT Madras. I am very happy to offer this online course on pericyclic reactions and organic photochemistry. Both these topics, pericyclic reaction and organic photochemistry, are offered in the postgraduate level chemistry programs, particularly in MSc chemistry program. So if you are in the final year BSc chemistry or MSc chemistry program, or if you are doing a PhD program in chemistry, you will find this course very useful. This is the first module of this particular course, and I would like to introduce the concept of activation of chemical reactions by a couple of examples here. Before we go into that, let us see what are the course objectives. This course is essentially on two important topics, namely pericyclic reaction and organic photochemistry. So essentially, going through this course will make you an expert in these two areas. To understand the fundamental concept as well as the application in these two areas, this course is tailor-made to cater the needs of the students. What are the learning outcomes of this particular course? You'll be able to understand and appreciate the fundamental concepts in these two areas, namely pericyclic reaction and organic photochemistry, become very familiar with the reaction mechanisms of these two areas, and be able to apply the principles and the reaction mechanisms that you have studied or gone through in the process of organic synthesis or synthesis of organic compounds. To be able to understand the processes involved in certain processes like fission, photosynthesis, solar energy conversion, and OLEDs, photochemistry will help you understand the fundamental concepts involved in these important topics. We'll see some of these things at a later stage in this module. Now, what is an activation of a chemical reaction? You know that certain chemical reaction takes place spontaneously at room temperature. Some of them take place even at very low temperature. And some reaction needs to be given some kind of an activation like heat or light to be able to come over the barriers that it poses. Every chemical reaction, the reactant must have some activation, or it should be activated enough to cross a barrier so that it can reach the product state. And this is essentially dictated by the transition state theory or the activated complex theory of the chemical reactions. The reactant molecules that are usually at room temperature may or may not possess sufficient potential energy to cross over this barrier. In order to make them cross over this barrier, energy must be supplied to the reactants to make them more reactive. In other words, the collision between molecules to become more effective, one needs to apply energy. This application of energy can be done either by simply heating the sample, which is a thermal methodology, or through the irradiation using ultraviolet visible light, for example, which would correspond to the photochemical processes. So these are the two fundamentally important processes, namely for the activation of chemical reaction. One can either apply heat or one can use photonic energy to promote the chemical reaction. The pericyclic reaction has two components. One is thermally activated pericyclic reaction. The other one is photochemically activated pericyclic reaction. We'll see several examples of the photoactivation as well as thermal activation of pericyclic reaction during the course of this particular module or subsequent modules that may come in the future. Now, what are the fundamental difference between the thermal activation and photochemical activation? This is listed in this particular table. The difference is, in the case of thermal activation, it is done by supplying of heat. In other words, by heating the reactants, one reaches the barrier or overcomes the barrier of the chemical reaction. On the other hand, photochemical activation is carried out by irradiation through light. In other words, the photon energy is what is supplied in the form of energy for the molecules to overcome the barrier. In the case of thermal activation, predominantly the reactions proceed through the ground state electronic configuration. In other words, molecule exists in the ground state electronic configuration. Sometimes they may be excited to the vibrational levels, higher vibrational levels of the ground state may be involved in the reaction. Nevertheless, they always proceed from the ground electronic state. Whereas in the photochemical reaction, the applied photochemical energy essentially promotes the electron from the ground state to an excited state. So electronically excited molecule or atoms are involved in the photochemical reaction. So photochemical reaction essentially correspond to reaction coming from the electronically excited state of the molecule. In the case of thermal activation, one cannot have a selective activation. Let us take an example of a Diels-Alder reaction, where Diels-Alder reaction involves a diene reacting with a dienophile to undergo the cycloaddition reaction. So there are two components involved. One is the diene, the other one is the dienophile. Now when we do the thermal activation of the Diels-Alder reaction, one cannot selectively heat either the diene or the dienophile because they are in the same flask. So one needs to heat the entire mixture. So selective activation is seldom possible in the case of thermal reaction. Whereas if you are doing a photochemical reaction, different molecules absorb at different wavelength of light. So by choosing the proper wavelength of light, one can selectively activate one or more molecules in the system, and thereby selective activation of photochemical reactions is possible. Let us take an example of two molecules. One is a colorless molecule, the other one is a red colored molecule. Suppose if one wants to activate the colorless molecule, it essentially absorbs the UV light, so it can appropriately choose a UV wavelength to excite that particular molecule, leaving the red colored molecule unactivated. On the other hand, if one wants to activate the red colored molecule, one can do so by choosing the wavelength corresponding to the red color of the compound and thereby activating that particular compound alone in a mixture of two compounds. So selective activation is a major signature of the photochemical reaction, which is not possible in the case of thermal reaction. The case of thermal reaction, usually the ground state molecules exist in the singlet state, so the reaction takes place from the singlet state of the ground state molecule. On the other hand, photochemical reaction can take place either from the singlet state or the triplet state. Depending upon the spin multiplicity of the state, electronically excited state, one can have reactions arising from either the singlet state or the triplet state of the molecule. So these are the fundamental differences between the thermal activation and photochemical activation of chemical reaction. We will see more of these examples as we proceed through the modules. Now this is a simple potential energy diagram describing a reaction coordinate on the x-axis and a potential energy in the y-axis, for example. The reaction coordinate is essentially the progress of the reaction. Suppose if a bond is breaking, then this would correspond to the length of the bond that is being breaking. Or if a bond is being made in a chemical reaction, which is often the case, one can plot the progress of the reaction as the bond length variation when the bond is being formed in this particular case. Potential energy, of course, is the energy of the molecule that we are dealing with. You have reactant molecules at certain potential energy and the product molecule at certain potential energy. In order for the reactant molecules to come to the product stage, it has a barrier which is represented by this red arrow corresponding to the free energy of activation. In other words, unless the reactant molecules are sufficiently activated to go to the transition state, one cannot reach the product stage. In other words, there is no possibility to directly come from the reactant state to the product state without having to cross over the activation barrier. This is what is dictated by the transition state theory as well as the otherwise known as the activated complex theory. So this corresponds to the transition state or the activated complex of the reactant molecule going to certain, absorbing certain energy and going through this particular state, which is the transition state. Now, the overall change in the free energy of the molecule is represented by the blue arrow. This is a spontaneous reaction. In other words, delta G is negative because the product is at a lower energy state compared to the reactant. So overall, there is a loss of energy corresponding to delta G being negative value. This is a reaction where the reaction essentially goes to the product without the involvement of any kind of an intermediate stage. Only a transition state is involved. Such reactions are known as concerted reactions, where no intermediate stages are observed during the course of the reaction. Now this is a typical potential energy diagram for a photochemical reaction. In a photochemical reaction, the ground state molecule initially absorbs certain photons of a definitive wavelength corresponding to the absorption of the molecule R, which is a reactant molecule. In doing so, it is electronically excited from the ground state to the excited state. R star represents an electronic isomer of the R. In other words, the electron distribution in the ground state and the electron distribution in the excited state are different. So they are basically electronic isomer is what we can refer to. And once it reaches this particular state, the excited state molecule will come back to the ground state by means of relaxation. And one of the relaxation is essentially losing energy to the surroundings and reaching certain point which corresponds to the transition state of the reaction. And once it reaches the transition state, it can go either to the starting material or it can go to the product. Since we are continuously irradiating the starting material, more and more of it will get excited. So eventually the entire process will be driven to the formation of the product in the process. Once again, the delta G dagger is essentially the free energy of activation of this particular reaction, and delta G R is the free energy change of this chemical reaction. This is the chemical representation, equation-wise representation of the photochemical reaction. Initially, the reactant absorbs the photon, goes to an excited state, which is an electronic isomer of the ground state. From the excited states, undergoes many processes, including radiative, non-radiative processes, which we will see in detail later. And one of the pathway it can take is to go to the product, which is a chemical reaction. So this is a absorption of light energy followed by a chemical reaction is what drives the photochemical reaction in most instances. Now, the most common pathway for chemical reactions, one can take a stepwise process or one can take a concerted process. Essential difference between a stepwise process and the concerted process is, in the stepwise process, there are intermediates that are involved here. Let us take this photochemical reaction. We already mentioned the starting material or the reactant absorbs the photon and goes to an electronically excited state. From the electronically excited state, it can either dissociate into a radical pair, or it can form a biradical, or it can form a zwitterion. These are the intermediate stages of the chemical reaction. And from this intermediate stage, a thermal process takes place corresponding to the product formation. So the electronically excited molecule essentially loses energy in forming the reactive intermediate species, and from the reactive intermediate species, the product is being formed in this reaction. On the other hand, if you consider a concerted process, this is a process where no intermediates are observed. Essentially, the reactant goes to the excited state and then goes to the product directly. If it were to be a thermal process, the reactant will directly go to the process through a transition state instead of an excited state, for example. So that is also considered to be a concerted process. Now, when the reactant goes to the product, it can go through a radical pair where two radicals are formed simultaneously, or it can form a biradical. Biradical is essentially two radicals on the same molecule at two different centers. If they are separated by n number of atoms, then you call it as 1n biradical. If it is separated by three carbon atoms or three atoms, in general it will be 1,3 diradical. If it is separated by 4 atoms, it will be 1,4 diradical, and so on. So biradical is essentially two radical species that is present in the same molecule at different centers separated by a number of atoms. Zwitterions, of course, are ions where you have both the charges being present, plus charge as well as the minus charge, and these are essentially polar intermediates that are formed during the course of the chemical reaction. So the photochemical reaction can essentially go through any one of these radical mechanism, or a biradical mechanism, or a zwitterionic mechanism before it goes to the product. The point that is covered in this particular slide is that one can have chemical reactions which are taking place through stepwise process involving intermediates, or the chemical reaction can also take place in a concerted manner without the involvement of any kind of an intermediate. So that is a message that I want to convey in this particular slide. Now, the concerted reactions can be either thermal reaction or photochemical reaction. We have examples of concerted reaction both under thermal as well as photochemical condition. Now, coming back to the concerted reaction, these are reactions which proceed through a transition state without the involvement of any kind of intermediates. Both the thermal type as well as photochemical type concerted reactions are known, and there are two types of concerted reactions. Those reactions which involve a cyclic transition state, and those reactions which do not involve any kind of a cyclic transition state. So whether the transition state is a cyclic transition state or an acyclic transition state makes the classification of the two types of concerted reaction. The ones that proceed through the cyclic transition states are the ones that are known as pericyclic reactions, and the ones do not proceed through the cyclic transition states are not pericyclic reaction. The examples can be given in the form of E2 elimination and SN2 substitution reaction, which are concerted reaction, but they do not proceed through a cyclic transition state, so they will be just a normal concerted reaction. Whereas reactions like Diels-Alder reaction or Claisen rearrangement, which proceed through a cyclic transition state, are known as the pericyclic reaction. The example is illustrated here. Consider the reaction of an E2 elimination reaction, where the base subtracts this hydrogen with the simultaneous loss of the halide or the leaving group X minus going out of the molecule. Here, the CH bond breaking as well as the CX bond breaking take place simultaneously, That is why it is a concerted reaction. But as you can see, the reaction mechanism does not involve any cyclic structures of transition state structures of this particular elimination mechanism. So this is a concerted reaction, but non-pericyclic type concerted reaction. Whereas if you consider a Claisen rearrangement reaction, the Claisen rearrangement is essentially a rearrangement of a allyl vinyl ether into a gamma delta unsaturated carbonyl compound. And you can see here it has to go through a cyclic kind of a transition state in order to form a bond between these two carbon centers. If you follow the cursor, you understand the formation of this particular reaction. With the breaking of the carbon-oxygen bond and formation of a carbon-carbon bond, it proceeds through a chair type of a transition state, cyclic transition state, and that is why this reaction is a pericyclic reaction, because it proceeds through a cyclic transition state and it is also a concerted reaction. These are the two necessary criteria for terming a reaction as a pericyclic reaction. Let's move on. Now, why does one need to study pericyclic reaction? Pericyclic reactions once upon a time were considered as no mechanism reaction because no intermediates could be found in this reaction. People thought these reactions don't have any kind of a mechanistic details involved in order to be able to identify reactive intermediates and so on. However, pericyclic reaction turns out to be the richest in reaction mechanistic details and stereochemical details. In order to understand the mechanistic details of this pericyclic reaction, it is necessary to study them. Pericyclic reactions are extremely useful reactions in organic synthesis because they are highly stereoselective and regioselective in nature. So the selectivities that are involved in the pericyclic reaction is what makes them very attractive in organic synthesis. So in order to make use of the high selectivities of the pericyclic reaction in organic synthesis, it is necessary to understand their reaction mechanism, how they proceed, and what kind of interactions take place within the reactive molecule and so on. So this is what essentially drives one to study the pericyclic reaction. There are quite a lot of pericyclic reactions that we will come across in due course, and during the course of these pericyclic reactions, one will learn a lot of details of the mechanistic as well as stereochemical aspect. So some basic understanding of reaction mechanism and stereochemistry of organic compounds would be extremely helpful in understanding the pericyclic reaction. Now, why do we need to study photochemistry? This is a question that one needs to ask before proceeding further. If we consider important processes like the vision, in other words, the sight of seeing something, there are some photochemical reactions that are taking place in our eyes. And these photochemical reactions are extremely simple reactions happening in a fairly complex system in the biological system. In other words, the simple organic molecules photochemistry, if we can understand properly, then one can extrapolate the processes that are involved in simple organic molecules into larger complex biomolecules. The sensation of vision essentially is because of a molecule called retinol, which undergoes a cis-trans isomerization that is triggered by absorption of a photon. So if one understands the cis-trans isomerization process of a simple organic compound, then one should be able to understand what is happening in the process of vision also. Similarly, for example, the synthesis of vitamin D that occurs under our skin, for example, when skin absorbs light, certain transformations take place in steroidal kind of molecule, which essentially leads to the synthesis of vitamin D, which we will see at a later stage when we talk about the photochemical reaction. Photosynthesis by plants, for example, has been happening ever since the earth was created, and this photosynthesis, where the carbon dioxide is converted into sugar molecules by means of absorption of light using certain material like the chlorophyll and so on, the plants are able to do the photosynthesis very efficiently, and this is an important process. And if one wants to understand the electron transfer processes that are involved in the photosynthesis, then basic photochemistry understanding is extremely important to understand these complex molecules. Now, if you look at the contemporary research in photochemistry, these are the topics that are listed here. One is the conversion of solar energy into useful forms of energy. In other words, conversion of solar energy into, for example, electrical energy by means of photovoltaic cells. And this is essentially conversion of photochemical energy into electrical energy. And what are the chemical reactions that are involved in the conversion of a solar energy into photochemical energy? One can understand if one understands the basic concepts and reaction mechanisms involved in organic photochemistry. The use of organic light emitting materials is happening quite often now. In fact, the cell phone displays now, you have the AMOLED display, which is amorphous material, organic light emitting diode material, is what is coated on the cell phone screens to be able to have the colorful displays that you see in the cell phone. This is essentially an organic molecule emitting light. Normally, photochemistry involves the emission of light after the absorption of photon. If certain molecules emit light, then we call it as emitting materials. The emitting materials can be either fluorescent emitting material or phosphorescent emitting material, depending upon where the emission is taking place from. And such materials, emitting materials, are what are useful in the OLED application. In other words, photochemists are the one who develop the molecule which are emitting in light and study the property of emission of light by means of photon. If the same process can be simulated by means of applying electrical energy, then you have electroluminescence, which is responsible for the actual OLED application. So the basis or the fundamentals of the OLED application essentially originate from the photochemical research in certain laboratories. For example, development of fluorescence-based sensors is another important aspect of photochemistry. Here, fluorescent molecules are used for sensing applications, sensing toxic elements like, for example, mercury, cadmium, nickel, and so on, arsenic and lead, and so on. These are fluorescence-based organic molecules where the fluorescence can be either enhanced or quenched by the sensing application that it is involved in. We'll see a lot of examples of this kind of fluorescence-based sensors during the course of our lectures. Finally, from the fundamental understanding of the photochemical processes, there is a topic called ultra-short laser spectroscopy, where a short pulse of laser is being applied, where the photon energy is being applied, and the reactive intermediates that are formed is studied in the very fast time scales of nanosecond, picosecond, or femtosecond time scale. Nanosecond is essentially 10 to the power minus 9 second, picosecond is 10 to the power minus 12 seconds, and femtosecond is 10 to the power minus 15 second. Such ultra-fast processes or the reactive intermediates that live only for such a short duration can be easily studied by means of the laser spectroscopy. Some aspects of this also we will see during the course of our lecture. Now, the resource materials are given here. There are two books that I would like to recommend for the topic of pericyclic reaction. One is a Oxford Chemistry Primer on pericyclic reactions by Ian Fleming. This is a thin book. It is a very nice book to read and understand, and I would recommend this particular book. One other book written by me on pericyclic reaction. This is a textbook, and this book essentially covers the reactions, their applications, and certain aspects of the theoretical aspects of the reactions are also covered in this particular book. So both these books will be extremely useful for this course. Most of the examples are taken from these two books, primarily from the book that I have written in pericyclic reaction, as well as the book written by Ian Fleming. I have taken some examples from this book also. As far as photochemistry is concerned, organic photochemistry is concerned, the book written by Nicholas Turo, V. Ramamurthy, and J.C. Scaiano is an extremely useful book. This is one of the most modern books that are available in the organic photochemistry. The topic of the book is Modern Molecular Photochemistry of Organic Molecules, covers the theoretical aspects as well as the reaction mechanism, and the practical aspects of organic photochemistry is covered in this particular module. So during the course of the next few lectures, we will start with the pericyclic reaction and then finally go on to the organic photochemical aspects of photochemistry of organic molecules we will cover at a later point. I hope you enjoyed this particular module, and I hope you will enjoy the subsequent modules also that I would like to present on the two topics of pericyclic reactions and organic photochemistry. Thank you very much for your attention.